The chart shows how the evolution of various programming languages took place. You can see how Fortran 1 led to Fortran 2, and in turn to Fortran 4, Fortran 77, and Fortran 90, which is similar to predecessors in some ways, and very different in others. You can see how Algol's various versions led to the development of Pascal, and in turn to Modula 2 and Modula 3, as well as Oberon and Ada. You can see how Algol also led to Simula and Smalltalk, and how various dialects of BASIC led to Visual Basic. You can see how CPL led to BCPL, and in turn to B, to C, to C++, and to Java. And you can see how Lisp led to Scheme and Common Lisp. This kind of evolution has also happened to human languages, and explains why Spanish, Portuguese, and Italian are very similar, and how Russian, Bulgarian, and Serbo-Croatian are a lot alike. Except in those cases, it took centuries for this to happen. With programming languages, it has happened in only 50 years. A programming language is simply a way that we express how computation is to be carried out. Since programming languages are necessary to help express the ideas behind algorithms, it should be no surprise that their history parallels that of computers, and that the history is frequently independent of computer development. Few people today know who Konrad Zuse was, or what exactly Plankalkül was. But Zuse came up with a way to express numerical algorithms more than a decade before Backus and his group developed Fortran. And Alonzo Church's lambda calculus became the theoretical underpinning for much of the theory of computation and the development of programming languages. We have to understand that the need to describe calculations is ancient. This page shows an algorithm that is a description of how to calculate the width that appeared in cuneiform writing as adapted by Donald Knuth. We have the volume and the cross-section, but we can work backwards to find the width. But why does this work? Here you see the algebra that leads to this calculation. The volume and cross-section for this rectangular cistern is length times width times height plus length times width. If the length and height are the same, it becomes length squared plus length times width. We can factor out length times width to get length times width times the sum of length plus 1. We can substitute length equals 5, and this simplifies to 5 times width times 6 equals 120. Dividing 120 by 30 gives us the width, which is 4. The calculation is a little quaint, but it shows how even the ancients were thinking about how to do more involved calculations. Charles Babbage received a grant of £1,700 from the British Parliament to develop the difference engine, a machine that would automate many types of calculations. In the middle of the project, Babbage abandoned it to develop the more complex analytical engine, which would have been the first programmable computer had he been able to finish it. But having changed the project without finishing the difference engine, Parliament refused to grant him any additional capital, and developing and making the tools that he needed for the work were very expensive. Contrary to popular opinion, the technology to complete the analytical engine existed in Babbage's lifetime. It was a mechanical device and not electric. And the portions of the engine that were completed worked exactly as Babbage had designed them. Although the machine was never completed, this did not stop the Babbage protege, Ada, Countess of Lovelace, from writing programs for the analytical engine. For this reason, Lady Lovelace, who is Lord Byron's daughter, is considered to be the first computer programmer. Konrad Zuse was a German engineer who built the first electronic digital computer. This was done in Nazi Germany, and Zuse had to do so in his spare time, because the Nazis, in their limited intelligence, didn't recognize the potential value of the work. Although none of his computers survived the Allied bombing of Nazi Germany, his notes about the planned language of Plankalkül did survive the war, but they were not published until 1972. The language was never actually implemented. There are no Plankalkül compilers in existence. but the language included data structures such as arrays and records, and allowed for the use of invariants, mathematical expressions that will be true during the execution of certain spots in the program, a very useful concept in software design. This slide shows an assignment statement that sets the value of a sub 5 as a sum of a sub 4 and 1. This first line indicates that we are adding 1 to a value in the array A and storing it in the array. The second line shows that the subscripts for the two operands are 4 and 5 respectively, and that they are both n-bit integers. The language looks almost hopelessly clumsy by the standards of today, but it is important to remember that this was designed 12 years before Fortran and 24 years before C.